bank has a private key that I call T bank, for example. The bank has a public key, everybody know, E bank and M bank. I use RSA. Okay? And then you can see that if I want to withdraw some money from the bank, then this is basically Alice want to withdraw some money from the bank. What Alice will do is Alice will send $100, for example, this is M. And then what the bank will do is, the bank will sign this $100 using DB and send this S back to Alice. Do you understand? So now you can see that when Alice actually spent this S to the merchant, Alice has to send M and S, right, to the merchant. But in this case, the bank will know that that is actually the coin that he signed before. Right? So that's actually what we want to avoid. What we want to avoid is, we want to make sure that when the bank signs this, then the bank actually doesn't know what he's signing. To illustrate this one in the real life, this is like this. There has been like a paper, carbon copy paper. I don't know whether you have seen, I think you have seen this kind of paper. So this is like a 2-layer paper in which what you do is, you cannot see anything at the top, and then you need to sign. There's a box there. You need to sign. After you sign, you can fill the top one, and your signature will be attached to the document. Have you seen this kind of paper? That's basically the blind signature. Okay, so the blind signature, the idea is, we want to make sure that what Alice will send to the bank will sign. But the bank will not know the contents of the message that Alice sent. Okay, so that's is M. Alice doesn't want the bank to know what M is, basically. Okay, so how can we do this? To do this, actually, we can do something like this. This is called blind signature. Again, I will have DB, and EB and MB is published. Okay, the first step, Alice will select a random number R, which is less than MB. Alice will select this R. And then Alice wants M to be signed by the bank. Alright? So Alice will compute M bar equal to R times E multiplied by M modulo M. Okay, R times E multiplied by M modulo M. And then Alice will send M bar to the bank. You can see that now the bank will receive M bar instead of M. Remember, the story is Alice wants M to be signed by the bank. But Alice does not want to send M to the bank. Okay? So Alice will multiply with R to the E modulo M. And then what the bank will do is, the bank will sign as per normal. So the bank will sign. How can the bank sign using RSA? The bank will compute M bar to the power of DB modulo M equal to M. Right? And the bank will actually send, I call maybe S bar, send this S bar back to Alice. Then the last step, Alice will compute S bar divided by R. If you give the S modulo M. Why? Because you can see that what is S bar. So when I say the reason is the following. What is S bar? S bar is M bar times to the power of DB. Okay, modulo M. What is M bar? M bar is R to the power of EB, DB, R to the power of EB, M, DB, modulo N. This means R to the power of EB times DB multiplied by M to the DB. Okay? So you can see that, remember, EB times DB is equal to 1, right, in RSA. So this is equal to R times M to the CB, modulo M, right? So that's why when I do S squared divided by R, this is actually equal to R plus M dV divided by R, which is M to the dV, which is a signature of the bank on M. You can see that the bank has never seen M, but now Alice will acquire M to the power of dV. So this actually is a very nice scheme due to David Chong. So David Chong created a company that is called DigiCash. If you Google it, it's called DigiCash. That's the one that makes David Chong rich. So people actually start buying this electronic coin because everybody believes that with this coin, your privacy is still preserved. When you want to buy something, you do not need to let the bank know.